finishing out section 9.2, we have a couple of things looking at how vectors really can interact with each other, how that could be applied to some physical situations. So I'm going to start with the notion of two vectors. I'm going to call it u and v. I'm going to put a little angle theta in between the two of them. And what I'm curious about is, now in this case I made v horizontal, it certainly doesn't have to be, but u is pulling this direction. So if I think about it as it related to that airplane example we saw earlier, we could have part of the force going this direction of u, part of it's really going this way, part of it's really going this way. How much of it is going in the same direction as v? We can kind of think of that as being a way to represent just what's happening along there. And what we call this is the component of u along v. And you can define it to be the magnitude of u times the cosine of theta, where we know the angle between these two vectors. What's neat is that with a little bit of algebra, we can actually represent this using a dot product. So if I start out with just the magnitude of u times the cosine of theta, so I start out with just that component, and if I multiply and divide by the magnitude of v, I get the magnitude of v, the magnitude of u, cosine theta, over the magnitude of v. But cosine theta, we had a definition for that in terms of a dot product. So this is really magnitude of v, magnitude of u, times u dot v all over magnitude of v, magnitude of u, over magnitude of v. And I get cancellation there. Those are all scalars. So I'm left with u dotted with v, all divided by the magnitude of v. It's a nice way to compute the component of u along v. So, for example, if suppose u equals 1, 4, and v equals negative 2, 1. I can even try to represent these, assuming that we're putting them on a nice rectangular coordinate system. Looks like u should go about like that, and v should go about like that. And so I'm really wondering how much of u is heading in the same direction as v. So we can do the calculation. U dot v over the magnitude of v. You see why the dot product is more useful here than the original definition, because I don't know what this angle is. I could work it out, but the trigonometry would get a little bit long, and this is quite a bit faster. So 1 times negative 2 plus 4 times 1 all over the square root, negative 2 squared plus 1 squared, and I get 2 over root 5. Now, when do you suppose you would actually get 1 in a situation like this? Here we got 2 over root 5. That gives us an idea of how much of u is going in the same direction of v. So it's a question worth thinking about. If you had something like this, you were trying to compute the components, when would you get 1? I'll play around with that a little bit. I think you'll find that u and v have to be not just the same, but the same and maybe even a specific length. So, worth playing with a little bit. But kind of an interesting an interesting side note to think about what this means and gives you a good geometric interpretation. So this component of u along v gave us just a scalar, in this case 2 over root 5. We have another notion, though. If I was to go back to my original drawing, I had v going like that, I had u going like that, and if I wanted to figure out, okay, not just what component of u is heading in the same direction of v, but could I actually come up with a new vector? And the name for that vector there, which its magnitude is based on the component of u in the direction of v, but it's actually now a new vector in the direction of v, written the subscript v of u, and this is the projection of u onto v. It actually gives us a new vector in this direction. So if we want to find it, we're going to start with the component. U dot v times v. And what that component does in terms of the projection, the component was really telling me, how long does this need to be? The component's giving me a scalar, it's giving me a magnitude. But I need it to be in the same direction as v. So what I can do, I can't just multiply it by v. That's going to stretch v out. But if I was to take v and divide it by its magnitude, I will get a vector of length 1 in the same direction as v. So we can write it this way, or u dot v over the magnitude of v squared, all multiplied by v. And this is the projection of u onto v. So a couple of different things we can do with this. If we need to just find the projection, so suppose u equals negative 2, 9, and v equals negative 1, 2. The projection of u onto v, u dot v, magnitude of v squared, all times the vector v. So this will give us a scalar. We'll multiply it by this vector. It'll be in the right direction. It'll be the correct length. So let's go through and calculate this. I'm going to get negative 2 times negative 1 plus 9 times 2 all over negative 1 squared plus 2 squared. Notice I'm computing a magnitude here, but computing its square. So I end up not needing the square root down there. Nice and convenient. And then I should multiply that all by v. Negative 1, 2. So, calculating that out, we get 4 times negative 1, 2. So the projection is the vector negative 4, 2. That's going to be a vector along the length of v whose magnitude is the component of u in the direction of v. Now, sometimes this is all we need, but there is one last thing that we might want. And it is to do what's called resolve u into two other vectors, u1 and u2. So I'm trying to break it apart into two vectors, and this means that u is equal to u1 plus u2, u1 is parallel to V, and U2 is orthogonal to V. And this resolving of vectors is useful in physics for computing work, for looking at forces that are going in different directions. So let's go to our same two vectors that we had before. So U equals negative 2, 9, and V equals negative 1, 2. Now, U1, it's got to be parallel to V, so that's just going to end up being the projection. U1 is projection onto V of U, and we calculated that on the last slide as negative 4/8. Well, now I need some U2 which is orthogonal to V. Turns out, though, that I don't need to start messing around with dot products to figure out orthogonality. I can certainly use them to check, but it's this that's going to be key. U is equal to U1 plus U2, so if I take U and I subtract U1, I better get U2. So U2 equals U, we subtract U1, so negative 2, 9, minus, get the brackets right, negative 4, 8, I get 2, 1. And you can verify with the dot product that 2, 1 and negative 1, 2 are actually orthogonal to each other. So that takes us through the end of 9.2.